In this last video, in lesson 7, we're going to be talking about decision making. And in this video, we're going to be using the unit normal table. So if you don't have it out, go get it out. You're going to need it. So we're going to review some key concepts. We're going to apply these concepts to decision making, and we're going to talk about something called score boundaries. So let's look at this statement. We can use the distribution of sample means, the DSM, standard error, along with z-scores, to make decisions about population means using samples. What this means is we're now going to be engaging in inferential statistics. We're going to make decisions about populations based on the samples we have in front of us. On the right-hand side of the screen, we have the normal distribution and we have z-scores on the x-axis. I'd like you to take out your unit normal table and find the z that has 0.025 in the tail. So what you're going to do is you're going to open up your unit normal table, look in column C for proportion in the tail, find 0.025, and then look over to the left to see what z-score corresponds with it. If you need to pause the computer, please do so. 1.96 is the z that is associated with 0.025 in the tail. And when we take 0.025 and we have it in two different tails, we can add those together to total 0.05 or 5% of the distribution. So these two tails right here are 5% of the distribution, 2.5% on the left tail, 2.5% on the right tail. This is going to be a very important area. We're going to call it our critical region, and it is our threshold for decision making. We're going to make decisions based on whether or not our sample mean can be found in the left tail or the right tail beyond negative 1.96 or positive 1.96. So z-scores that are unlikely to come from the population are viewed as different or extreme. So what does that mean? Well, in this case, since we've made our threshold plus or minus 1.96, anything less than negative 1.96 or more than positive 1.96 are going to be considered extreme values, extreme means. And what we're saying then, if our sample mean is in one of these critical tail regions, we're going to say our sample mean is not like the population mean. That what we're seeing in our sample makes it different than the population, that they're not one and the same, that our sample didn't come from that population, that they are actually part of a different population. So z-scores that are likely to come from the population are viewed as about being average. So what do we mean by this? These are all the calculated z-scores that are between that meaty middle area, between negative 1.96 and positive 1.96. We call these average. And if a score falls within this large meaty middle area, we say that our sample mean is actually the population mean. It's just a little bit different because of sampling error, but it is indeed the fact that it is the same as the population mean. So I've shaded the areas here, and you can see the tails of the distribution. What we're going to say is that if our mean falls within the shaded or critical region, that this is evidence of what we call a treatment effect. And what we're saying then is the mean of our sample is very different from the population. That whatever we did with our sample made it different than the population. There's a treatment effect. So the middle 95% are high probability values. I'm repeating myself a little bit here. So for example, the mean on this graph on the right is the population mean is 400. So that means any means that are within that white middle area are pretty much like that mean of 400. They might be different, but it's just due to sampling error. But once we get past a z of negative 1.96 or positive 1.96, we then start to say, you know what? It's so unlikely that we would find a mean from this population in these areas that we're going to take a leap and we're going to say, no, our population is not the same as our sample. Our sample is different. Something happened to our sample. There was a treatment effect, and they now are part of a different population. So I want you to look at your unit normal table in column C, and I want you to look at all the z-scores that are 1.96 or higher, so 1.97, 1.98, etc. The proportion in the tail, as you'll notice, is getting smaller, which means the probability is getting lower. The tail is shrinking. Higher z-scores mean lower tail areas. So low probability events demonstrate what we call a statistically significant difference. This is big. This is what we're going to be talking about for the rest of the course. This is a case where your population mean and sample mean are statistically significantly different, that they are not one and the same, that we're able to say that there is statistical significance. So we're going to use a scenario here to work all this out, and hopefully it'll make it really clear. A community health worker is interested in the effectiveness of a new practice at reducing the number of missed appointments each week at a community health center. So we don't know what the new practice is. Maybe they practice smiling more when people walked in the health center and then they wanted to come back. I don't know. So the average number of missed appointments in history for the health center is 45 with a standard deviation of 12. So this is what we call the population. The population is all the scores to this, all the average mean missed appointments to date. Mean of 45 and a standard deviation of 12. So let's just say that we have a random sample of 36 patients. We select them, and they're from a normally distributed population, and they participated in this new practice, whatever it is. And after they participated in the new practice, the average number of missed appointments in the sample was 40. So the population average was 45, but this new group of small sample of 36 patients, their mean was 40. 40 is less than 45. It looks like whatever we did had a treatment effect. But the thing is, we really don't know if it had a treatment effect yet. We don't know if the difference between 45 and 40 is real or if it's just sampling error, and they really are the same. This is where our decision making comes in. And so let's work this out. Before we get started, let's identify the independent variable and the dependent variable for this study. The independent variable is whatever new practice was implemented with the sample of patients. And the dependent variable is what we expected to change as a result of the independent variable. And that is the number of missed visits. So it's always important to kind of go through and make sure that we are aware of what is the independent variable and what is the dependent variable. All right, let's get started with the rest. To try to figure out if our mean of 40 is statistically significantly different from 45, this is all the information we need. Let's see what we have. We have the z-score formula for finding a z-score for a mean within a distribution of sample means. We have the standard error formula, which we need for the z formula. And then we know the population mean of 45, standard deviation of 12, our sample mean is 40, and the n is 36. From here on out, it's all smooth sailing. So let's find the z-score first. So our mean was 40, and the population mean was 45. We need to divide that by the standard error of the mean, which is over here. So to figure that out, the standard deviation was 12, and the square root of n, square root of 36 is 6. So our standard error is 6 goes into 12, which makes it 2. So our actual z-score for a mean of 40 is going to be 40 minus 45, which is negative 5, divided by 2, which gives us a negative 2.50. So that is our z-score. We've got that. So what we need to do now is plot it out to see if this is an extreme score. So let's do that. I've put together the distribution of sample means here with the z-scores. Our mean was 40, which meant a z of negative 2.50, but I'm going to remind you that our decision-making boundaries were plus or minus 1.96. So what I'm going to do is I'm going to draw a line about where negative 196 might be, And then I'm going to shade in this whole area, because if our mean has a z-score within this area, I'm going to consider it to be an extreme z-score. I'm going to do the same for the positive side. Got 1.96 about here, and I'll go ahead and shade that in. Now, we take a look at our z-score, which is negative 2.50. I'm going to evaluate it on this side because it's negative, and I'm going to go take it 2 and then negative 2.50 is somewhere around here. So this is where our z, our mean, is found. And lo and behold, it is in this critical region. It is more extreme than negative 1.96. So what am I going to say? I'm actually going to say that my mean of 40, which has a z-score of negative 2.50, is more extreme than negative 1.96. And therefore, I'm going to say that my mean of 40 is statistically significantly different than the mean of 45 that was in the population. What I'm saying is there was a treatment effect, that the people in this group are no longer the same as the people in the general population because they were beyond our critical boundary. And so let's take a look at this further. So let's ask 2 questions about these data. Is the result typical, or does it represent an extreme result? So is our mean of 40 typical, or is it extreme? And then I want you to be thinking about what values represent the boundaries that separate the 95%. So we know the z-scores are negative and positive and negative 1.96, but what are the actual means that are located at those z-scores? We're going to figure that out. Well, the answer to A you've already figured out. We already talked about how negative 2.50 is within that extreme threshold area, and so it is an extreme score. There is statistical significance. There has been a treatment effect. But for B, it's a little bit interesting. We want to know the mean boundaries that separate the 95%. So we can use algebra to solve for each boundary, and I'm going to demonstrate that. Or we can use a handy formula. Now I'm going to show you this formula, and you'll recognize it as being very similar to the formula that we used when we didn't know a score, but we knew the z-score, the standard deviation, and the population mean. So let's work these out. Okay, we're going to start off with a little bit of algebra to figure out what is the mean that is at a z-score of negative 1.96. Well, what do we know in this z-score formula? We do know the z is negative 0.196. That's the z we're interested in. So I'm going to put that down here, negative 1.96. Now, we don't know the mean, so I'm just going to put an equal, I'm going to put an m here. But we do know the population mean, which is 45. We do know the standard error from the last time we did this, which was 2. So now we're going to do algebra just to get m by itself so we can figure out what mean is at a negative 1.96. So the way to do that is I'm going to first multiply each side by 2 to get rid of this 2 on this side. So I'm just going to scoop this out to get rid of the 2, and when I multiply 1.96 by 2, I get negative 3.92. So I'm going to write that down, negative 3.92. All right. Now what I do is I have to get rid of this negative 45 on this side, and I'm going to do that by adding 45 to this side. But when I add 45 to this side, I also need to add 45 to this side. So 45 plus a negative minus 3.92. I'm going to do that real quick. So we have 49, 8, 0, 1. So we have 41.08 is the mean. So when we have our normal distribution, the mean at z equals negative 1.96 is 41.08. But I'm going to show you a different way to do it that's much easier. Okay, what we have here is a version of the same formula that we used when we didn't know the score in a z formula. This time we don't know the mean, but we can find this by using this handy dandy formula. So basically what I'm going to do is I'm going to take z, multiply it by the standard error, and add the mean. So easy enough. So our mean is equal to our z of negative 1.96 times 2 plus our population mean. So this is exactly the same thing that we did before. We have negative 3.92 plus 45, and that gave us a z-score of 41.08. So that is a faster way to solve for this missing m. So we did this for the negative z of negative 1.96. Let's do this now for the positive z. We're going to do the same thing for a z of 1.96. We're going to figure out what is the mean at z of 1.96 when you have a population mean of 45 and a standard error of 2. So we have the z-score formula here, but we don't have all the pieces. Let's fill in the pieces that we have and do algebra to figure out the rest. So our z-score is 1.96. I'm not going to put a positive there because I just know it is. And it's equal to some mean, this is the thing that we don't know, minus the population mean of 45 divided by the standard error of 2. So we know everything except for the mean here, and this is what we're going to find out. So we're going to start with algebra. To get rid of the 2 in the denominator, I'm going to multiply this side by 2 over 1 and this side by 2 over 1, basically. So it cancels this out. And when I multiply 1.96 by 2, it gives me, again, 3.92. This time there's no negative sign because I am multiplying a 1.96 positive by 2. Now I need to get rid of the 45 on this side to keep m by itself. So I'm going to add 45 here, and I'm going to add 45 here. And that cancels this side out. There we go, 48.92. So the mean at 1.96, when we have a population mean of 45 and a standard error of 2, is going to be 48.92. So I'm going to do this with our handy-dandy formula. Okay, again, here's that same formula we used a little while ago, and it's so easy to plug everything in. The mean is what we don't know. We have the z of 1.96. We have the standard error of 2, and we can add the mean of 45. So this is basically 1.96 times 2 is 3.92 plus 45 gives us a mean of 48.92. There you go. So I've given you a lot to think about in this lesson. And in lesson 8, we're going to be talking about hypothesis testing. And lesson 8 builds on this lesson. You're going to be doing the same types of calculations in lesson 8 that you did in this lesson. So that's good and bad. It's good if you understood this lesson. If you didn't, this is time to really make sure you go back, ask questions, make sure you understand what is in lesson 7. It'll make all the rest of the course so much easier. This is sort of a transition point. You want to make sure that lesson 7 and lesson 8 are understandable, and if they are, the rest of the course comes a lot easier. It's been my experience that students tend to breathe a little easier in the second half of the course. So let's do a quick lesson summary. First of all, we talked about how there is error between a sample and the population. And this error can be calculated, and we can use this error to determine the probability of finding our sample mean. So we use this probability to make decisions about how similar or how different a sample is from the population. So that is lesson 7 in a nutshell, and I look forward to speaking with you in the Hallway Conversations Forum.